So I've got 18 slides. We'll basically just work through and hopefully you all will do much of the talking to demonstrate your knowledge of these content areas, but that's essentially the approach I'm looking at. And so I've started preparing the exam and it should work out very nicely. I'm trying to use one data set for both the network screening and the different evaluation problems. And I'm also trying to set it up so that there aren't like an infinite number of ways you guys can do it, just because that makes it very challenging for me to grade it. But that is what I'm planning to do there. So you'll have one crash data set basically that can be used for those various purposes. And then we'll have a series somewhere from 3 to 5, like short answer type questions that would cover some of the big picture items we talked about early on in the course, basically. So that's what we're looking at in terms of structure. And then, like I said, as in the case of the 849 exam, you'll have the whole day to do it. It shouldn't take nearly that long. The most extensive part would probably be working through the analysis portion, trying to build the SPFs where applicable and so forth. So any questions on just the general structure stuff? Okay. All right, so I thought this was animated. I guess it wasn't. So nominal safety and substantive safety were some of the things we talked about initially on the first lecture period. And so do you guys recall what those terms mean generally when we talk about a roadway being nominally safe versus substantively safe?
If I remember correctly, I think nominal safety was like, oh, did I cut out there?
No, you're good.
It's like being safe on paper, like designing it to the right standards and that sort of thing.
Yeah, exactly. So when we talk about nominal safety, we're generally saying that the roadway is compliant with whatever the minimum standards and or guidelines would be for that facility type. And that could include, in the AASHTO Green Book, as an example, if you meet the minimum curve radius, the super elevation rate, etc. In the MUTCD, there are various standards for pavement marking, signage, things of that nature. And the same is true for various other guidance documents. And so we can make a general argument then, and part of that relates back to liability concerns to some degree. If we're not compliant with those, and I don't know that we actually talked about this at great length, but what happens if a roadway is not nominally safe? So if we don't actually meet some of those minimums?
Don't you have to get an exception from Federal Highway or some other agency?
Yeah, exactly. So I don't recall if that's your own knowledge or if we had talked about that in the class here, but there is a process for design exceptions. Or, oh gosh, I'm blanking on the term. It varies from state to state. There's a lesser, not quite to the level of a full design exception, because that would only be required for full reconstruction projects. And so if you've got like a 3R where you're doing just rehab or resurfacing or whatever the case may be, you don't need to bring it back up to AASHTO standards in that case, in that very narrow case. But anytime you go to full reconstruction, or you'd be constructing a new road, for example, you'd have to pursue a design exception if you don't meet those. But if standards change over time, and we're getting kind of in the weeds here to a degree, but you would need to document that and get approval from the FHWA, and that would relate to factors like the 10 controlling criteria for highway design, which I'm assuming you guys probably talked about in 449. And so when you guys took 449, that would have been after, because initially there were 13 controlling criteria and then they reduced it down to 10. Like there were a few cases like sag vertical curves. There's basically no evidence that there's actually increased crash risk in those cases. So there were a subset that were reduced, and I can't remember when those changes occurred. I want to say it was sometime 2017-ish. So you would have taken it after that, right? So anyway, sorry, I said I wasn't going to do much of the talking here, but yeah, that's a very good definition of what nominal safety is. In contrast, what do we mean by substantive safety? And I guess, Travis, if you're
so that would be more data driven, more reliant
right
on what the crashes are.
Yeah, exactly. So a more quantitative approach to highway safety, and this has really become a big emphasis, I'd say, dating back to maybe the late 1990s, but particularly the first decade of the 2000s with the publication of the Highway Safety Manual. And so that would include using more quantitative and predictive methods for safety. And those would tend to be more proactive rather than reactive. So historically, we just identify high risk locations based upon where crashes and or injuries and fatalities have occurred. And that tends to be it's not a bad approach, but it's not the most efficient or optimal use of resources in trying to identify those sites. And so we basically use the information from those individual sites, as well as information from a broader population of similar sites. And we would essentially blend what's observed versus what would be expected based upon those site characteristics, right? And so in practice, agencies will look to satisfy both the nominal and substantive safety aspects, but substantive and the quantitative data-driven approach is becoming a much larger part at present, okay? We haven't got into this in great detail, but when we talk about the 4 E's of traffic safety, do you guys recall what those E's are?
Engineering, enforcement, education, and EMS.
Yeah, exactly. And so we talked a little bit at a high level about the different types of strategies that are employed across those domains, and how some of those areas are more appropriate for addressing certain aspects of driver behavior versus others. And so if we think about, I guess we can kind of briefly go through each of those. Enforcement's a pretty easy one because it's a pretty narrow realm. And so what's enforcement typically useful for within a safety context?
Ensuring that people follow the rules that are set, like speed limits.
Yeah, so the enforcement piece, we're basically trying to target problem behaviors, right? And so that we typically would look at high visibility enforcement programs to enforce violations of traffic laws, with speeding probably being about the most prevalent of those, and then also areas like distracted driving, drinking and driving, etc. And then they play a supporting role to varying degrees in other areas as well, but the primary piece there is just enforcement of traffic laws. Education. Any thoughts on education? There's a few different perspectives where that's pertinent.
That has something to do with like the driver training programs for new drivers, I guess, and other different education, like all over YouTube is the NHTSA don't drive through a railroad crossing advertisements right now.
Yeah, I've been hearing those a lot on some of the podcasts I listen to as well. It's pretty funny. And so, yeah, those are the 2 primary elements. So the first is just the education as to safe driving practices, and that would include, to your point, the introductory driver training, graduated driver licensing programs, to a degree, continuation and renewal of those licenses over time, although there's not much of a formal reassessment in most states in that case. And so once you've got the license, the other piece is really that public outreach and public awareness piece that you had alluded to there. And so those are the primary areas where the education piece is important. Let's see, EMS. How does EMS play a role?
I would say it's kind of the word you said was a supportive role, like I guess making sure that for the small amount of severe injuries, fatalities, that they can respond timely and appropriately.
Yeah, right. So it's largely a support role. So as the a great definition there, basically. So when crashes do occur, basically responding to those crashes, helping to clear the scene. Now, that's kind of a role of not just the EMS folks per se, but law enforcement. That would be kind of a secondary role for them as well. So that there aren't any, so we're minimizing the risks of secondary crashes and incidents. But the primary role of EMS is just to respond and try to address injuries and mitigate the severity there. And so we'll tend to find that that's a particular concern. I'm assuming we talked about this in rural settings, particularly where if you're in a crash in the Upper Peninsula, as an example, the response time is going to generally be a lot worse as compared to more urban areas of the state. And we've seen a lot of advances with things like OnStar and some of those in-vehicle safety features that have actually done a pretty good job at helping to reduce those response times, particularly in those more rural environments. But that's the primary role of the EMS side. And then engineering, I mean, I guess it's largely implicit. And we've talked about a lot of these, and we'll continue to review some of those today. So I think we'll table that and incorporate that discussion to the remaining pieces here, though. Okay, a whole bunch of acronyms, as are common in transportation broadly, and then in safety specifically as well. So what's the HSM?
Highway Safety Manual.
Okay, and can somebody give me a 50,000 foot perspective? So what is the Highway Safety Manual?
Sort of like the standards and guidelines on how to properly engineer the highways, I guess.
Okay, so I would be somewhat reluctant to use one of the words there. So if we think of standards versus guidelines, it's not a standard per se. So it's basically a best practice. Agencies aren't required to use it. Although I should step back a little bit there. I guess agency by agency, I guess some agencies have directly incorporated into their policies that you have to use either the HSM or some tools developed based on the HSM. But generally speaking, it's a guideline, right? So it's based on research, and it's providing essentially models for how to, at least science-based models on how to most effectively address highway safety in a quantitative manner. Okay, and we talked about the various aspects there, and so that would include and hold on, I'm going to skip ahead for 1 sec here. I can't remember if I'm going to talk about this. No, I won't talk about it on the next slide yet. So when we talk about the Highway Safety Manual, there were a few general areas. Now the first of those that we talked about was network screening. Can somebody remind me what network screening is?
Finding out which locations require attention to make improvements.
Yeah, so basically we've got a population of roadways that are under the jurisdiction of any given agency. And so agencies have a increasingly finite amount of resources available to address those safety problems. And so as a consequence, they need to be able to effectively identify the sites that have the most promise for reductions of crashes, injuries, fatalities, et cetera. And so we talked about a few different methods there, and we'll get into those on the subsequent slide, but that was one of the big pieces we've talked about up to this point. Once we've identified those locations, there are a series of different projects that could be implemented, and we've talked about evaluation of those projects, and we'll get to that a couple slides from now when we talk about before and after type study designs as an example. And then there are a few other areas we haven't really got to yet that we'll get to later on in the semester, like trying to identify appropriate countermeasures for some of these crash patterns that we observe and things of that nature. But okay, HSIP and SHSP. So those two items are largely related to one another or integrated from an agency or from a state perspective. And so does anybody recall what HSIP stands for?
The Highway Safety Improvement Program?
Yeah, so HSIP is the Highway Safety Improvement Program. And that basically would involve, planning, design and operation of the facilities, and then evaluation over time. And so that's largely a cyclical process that would be inclusive of those areas we just talked about. So the network screening piece, the comparison of different candidate projects, selection of projects, and then evaluation over time. And then you basically iterate through that process. And so each state is required to have an HSIP in place, and they'll submit reports annually to the FHWA. And so Michigan and every other state will submit a report on an annual basis as to which projects are funded through that program. And as a part of that, they would also provide evidence as to the effectiveness of that program over time, typically through a comparison of before and after crash data in those instances. Okay. And that relates back generally to the SHSP. And what's the SHSP?
The Strategic Highway Safety Plan.
Yeah, Strategic Highway Safety Plan. And so that's basically a governing document for that each state has in place. And there's a national document that was developed by AASHTO. And at a more local level, we'll even see individual agencies or regions would develop their own highway safety plans as well. And so what's included in a strategic highway safety plan generally? What type of information?
Does that have to include like the specific sites where problems are occurring, and then also like specific ways that that agency is going to be evaluating and analyzing any changes to those sites?
In part. So at a big picture level, so anytime you're developing, sorry, my dog, it sounded like he was going to throw up all over the floor. Fortunately, he did not. I've lost all track of. Okay, so the SHSP. So anytime you're developing a plan, it generally would have some kind of overarching goal. And so that's one of the critical elements here is states are responsible and actually required by federal law now, based on, I think that was safety, was it Safety or MAP 21? I forget which legislation actually required the development of specific performance measures that would allow for tracking progress towards these goals over time. And so typically most states have adopted a similar ultimate goal. And I think we talked a little bit about this. And we talk about towards zero deaths as an example. And so obviously that's very high level. And, as we look at progress towards that ultimate goal, we have a series of shorter term and probably more reasonable objectives that would be based on reductions in fatalities or crashes or crash rates or fatality rates or any various combinations thereof. Okay. And so basically states are required by law to update this plan at least once every 5 years is how it's set up currently. Here in Michigan, I think we've been operating on a cycle of, well, it was every 3 years or so. Now it might be closer to 5 again. But basically you're using data to update those metrics over time. And then in concert with that, I guess, Jordan, to your point you were working on there, the SHSP basically identifies areas that are particularly problematic or where there are opportunities for realizing benefits in terms of crash reductions or fatality reductions. And so if we think about those, a lot of those emphasis areas are pretty similar from state to state. And there are a few that are probably unique to individual states, but can you guys recall any of the emphasis areas from either the national or the Michigan SHSP? They're quite similar in terms of those topic areas, but does anybody remember? So think about types of crashes that are disproportionate in terms of contributing to fatalities, certain types of problem behaviors or problem drivers? Oh, you're muted if you were.
Yeah, I was wrong screen. I would say, I mean, targeting reduction of drunk driving crashes.
Yeah, so from a behavioral standpoint, drunk driving has been a longstanding concern. Restraint use as well. We've got regular and recurring programs in those areas. Aggressive driving is another example. Now that one, it's a rather broad term there, but that would include things like speeding would be the one that's most directly addressed generally, but also, tailgating, things of that nature. Groups of or I shouldn't say groups of drivers, but groups of road users that are overrepresented in severe crashes. Any thoughts there as to specific groups?
Pedestrians and bikes.
Yeah, so peds and bikes have been a big emphasis, and really nationally, because we're still seeing, I just saw statistics earlier this week where we saw it might have even been record levels in terms of ped and bike fatalities in much of the country, despite the lower levels of travel during the pandemic in 2020 specifically. And that's been an issue here in Michigan as well. So you're probably aware we've got a number of projects right now. We're working with MDOT to address the ped and bike issue. Outside of that, motorcycles continue to be a big problem area nationally if we compare that to other types of vehicle crashes. And so those groups would comprise the most vulnerable group of road users. And then beyond that, there are other types of groups, and this is where we're looking more at specific subsets of drivers who tend to have higher crash risks on a per mile traveled basis. And who would those groups include? So if we were to look at based on driver characteristics, what types of drivers tend to be the most crash prone?
I would venture to say, well, I can say young, like the youngest and the oldest drivers, and I would probably venture to say males probably getting more crashes.
Yeah, so generally speaking, we see a U-shaped curve with respect to age, and so younger drivers and older drivers are typically focus areas in a lot of these plans. I've not seen anything programmatic necessarily that would relate to gender or sex necessarily, but and it's kind of interesting when you look at the research literature. We're going to go on a big tangent here, so I'll pull it back, and we'll talk about that in a subsequent lecture. But I guess the one point I'd note there was a lot of the literature had consistently shown that females were more likely to be injured in crashes than males, and even at the lower end, so minor injury or severe injury. But there's actually been some research that's shown that there's kind of an inherent bias there. Where officers will tend to code the injuries to females more severe than males. And there's various reasons for that, implicit and explicit biases that come into play there. But anyway, we're going to go on a major tangent. That's typically not something that's directly addressed. But some of the areas, I guess, if we think about why there's a perception of males being higher risk, it would relate to some of those other, problem type behaviors we had talked about previously. So. But typically on the driver side, it's those older and younger drivers specifically. And then on the engineering or roadway side, here in Michigan, I think we talked about how historically there had been two action teams. One was an intersection safety action team, and then one was basically a roadway departure action team. And those have been combined into TSEAP, I think is the acronym, which is just the Traffic Safety Engineering Action Team, if I'm remembering that acronym correctly. And so they meet on a quarterly basis and basically are responsible for kind of coordinating and disseminating information about best practices based on national and then state specific research as well. Okay, so all those pieces kind of fit together into that strategic highway safety plan. And so it outlines these focus areas, and then it also indicates specific strategies and specific groups among those 4 E's, for example, who play important and leading roles in those areas. Okay. And so, like I said, those plans are updated on roughly a 5-year cycle, and they kind of work in concert with the HSIP. And so, generally speaking, the strategies that are emphasized and the goals that are emphasized in the SHSP are also then integrated into the HSIP, and it's kind of like a cohesive, integrative approach then ultimately. Okay. And then the last 2 items, it's been a few weeks since we've talked about these, but do either of you recall what MUC or MIRE are within the context of highway safety?
It's Model Minimum Uniform Crash Criteria.
Did you know that, or did you pull that from your notes?
That's on my notes. I didn't actually remember that.
I was going to say I would have been thoroughly impressed, because usually people don't remember if the model or the minimum comes first. It's the model in this case. But so, do you recall what exactly that entails, or why that's useful, Travis, when we talk about those model minimum uniform crash criteria?
So it's the standardized set for describing the crashes. I don't know how.
So if we think about just the terms that are included there, so model, minimum, uniform, uniformity. Why is uniformity in crash reporting important?
So we have like a basis to compare the crashes to.
Yes. So if we think about uniformity, what do we mean, or how would crash data be non-uniform if we go back historically, like let's say 50 years ago? Although if we went back even 20, we'd probably see quite a bit of non-uniformity. But in what nature would we say that crash data were non-uniform? And I apologize, I don't know how to state that question and not have it be somewhat ambiguous, but so I get either of you any thoughts? So when we think about uniformity, we're largely talking about uniformity in terms of the crash report forms and also the crash reporting process. And so if you think about non-uniformity, we tend to have very good uniformity within a state, as an example, right? And does that, can you guys elaborate on that point a little bit with me giving you that little bit of a prompt?
So I guess like the law enforcement within the state is like receives the same training on how to go about it, and if it's different between states, they could have different ways of filling out the same form.
Okay. So yeah, training is an element of that. But if we go back to the actual forms themselves, so if you think about when these forms were first developed, and that's an interesting question, and I'm just talking to myself at this point, but I've never seen like the original old school crash report forms. But if you looked at the older forms, they would tend to be quite a bit different from state to state. And that was the reason why the model minimum uniform crash criteria were introduced, is because if we think about this from the perspective of NHTSA or the FHWA, there are various reasons why uniformity is important. In part, these data are used as a funding mechanism in some cases. They're also important if we're trying to conduct comparisons of safety performance across states, as an example, okay? And so if we think about different types of programs, like let's say Michigan's a primary seatbelt use law state. I came here, well, I'm from Michigan originally, but I came back from Iowa and I did my grad school in Indiana, and both of those were secondary law states. And there are various reasons for that. But if we wanted to assess the efficacy of primary belt use laws, there are a number of factors that would play a role there. And so as an example, if we're trying to assess the effectiveness, and I guess let me check real quick. Do you guys have a back-end constraint on this? Because I can see we're rambling. I guess it's more I'm rambling here, but we got a bit of content to cover. So I'll try not to belabor it here, but if we're looking at, say, for example, belt use laws, we would typically rely on crash data to make comparisons across states. And so there is still some inconsistency. Virtually every state, you'll have detailed injury information on the crash involved driver. Even if that driver is not injured in the crash, that'll be recorded as a no injury event. Okay. Now, if we go to the passengers, those data are not collected consistently across states. And so, for example, some states don't collect data for passengers who aren't injured. And that presents a bit of a problem, because then it's not an apples to apples comparison when you're trying to assess injury outcomes, right, across primary and secondary law states. And so, like here in Michigan, and apologies if I've already told you this story, but back in, gosh, it was probably around somewhere in the 2009 to 2011 timeframe is when we had introduced changes to our child restraint laws here in the state. And prior to that point, Michigan didn't collect data on uninjured passengers. And I forget if it was just in the back seat or all uninjured passengers. And so it was very difficult to try to ascertain effectiveness through a before after type study design, because prior to those law changes, there wasn't that mechanism. Now, subsequent to that, what they've done is basically, they used to, on the crash report form, in the earliest case, they would just have whether or not the person's belted. Okay. Now for children, that's not sufficiently detailed for us to be able to inform any of these child restraint programs. And so eventually they changed that so that they had belted, not belted, or child seat. And it gets significantly more nuanced. And I don't know if either of you guys have participated in the child restraint studies that we do historically here. But even in that child seat category, you have child safety seats, you have forward-facing booster seats, you have you have high back boosters, you have backless boosters, you have forward-facing child restraint seats, you have backward-facing child restraint seats, and there are certain criteria that dictate when children should be restrained in each of those different device types. And so they had actually added additional crash codes so that we get some additional granularity there in that case. And so that's one very specific example. But there are a wide range of cases where that consistency is particularly important, especially when we're trying to make comparisons of different programs across states. So anytime we're trying to compare trends within states, it's usually relatively straightforward, because there tends to be fairly good consistency there. One caveat there, so in Michigan, if we go back, I don't know, maybe 10 to 15 years ago, we probably had about 40% of the crash reports being submitted electronically at that point, and now we're probably pretty close to, and maybe we are, I'd have to look at the data, at near 100% electronic reporting currently. And so as a part of that, there have been some changes and some improvements, because as you go to the electronic forms, we can build in logic checks and more efficient quality assurance, quality control type procedures. And so I guess the big point here, that uniformity is important just largely for evaluative purposes and for tracking and for measuring performance. Okay. And so that was the basis for developing this, is that there were significant differences across states particularly. And so now, gosh, I'd have to look, but I know there have been a few studies the FHWA has engaged in just to assess practices across states. And so uniformity is really quite good now at a big picture level, but there are still some states that wouldn't necessarily collect data for all crashes like we do here in Michigan, or would have different minimum reporting thresholds and things of that nature. So those are a few of the things to consider there. Relatedly, when we look at MIRE, does anybody recall what MIRE stands for? Without looking at your notes, I'd be more impressed, but if you must, that's fine as well.
It's the model inventory of road elements.
Yes, exactly. And so that basically is similar to the model minimum uniform crash criteria. The model inventory of roadway elements is basically providing guidance as to the most important data characterizing the roadway network in each of these states. And so that would include just very simple fundamental things like where the crashes are located. So it wasn't until, gosh, I can't recall which legislation, if it was the FAST Act or MAP 21, but it's been within the last 10 to 15 years that there was a requirement that all crashes are locatable. So prior to that, many states, we did have fairly robust databases, but if you look at states that are very rural in nature and don't have the resources, there were some significant gaps back then. And so that's one of the critical elements is we need an actual database that geolocates where all these roadways are. And that helps us to make informed decisions as to the safety practices, right? And then beyond just knowing where the roadways are located so that we can place the crashes and other information, there are certain characteristics of those roadways that are important for evaluation and predictive purposes. And so what would some of those elements be? Or what would you say the three most important elements that should be in a roadway inventory database aside from the location information? Any thoughts?
The speed limit should probably be included.
Speed limits are good. You would probably be surprised at how many states have problems with that. So we've done a lot of work with the Sharp 2 study, right? And you guys are familiar with the naturalistic driving study database, right? So we've got extensive roadway information across 6 states, but we don't have speed limit information included. We have point information for speed limit signs. And so we can use that to infer speeds, which seems super easy and trivial, but it's actually, I had grad students spend a very long time trying to conflate various elements in GIS to integrate that information. But yeah, speed limit is definitely important. In addition to speed limit, what else? If we think about it from a safety standpoint, what would the single most important element be if we're trying to predict or forecast safety performance on those roads?
Traffic volume.
Yeah, so traffic volume is a huge one. And I don't know the extent to which you guys are aware, but we're having major issues with MDOT's traffic volume right now for the purposes of our speed limit project because they changed vendors a couple of years ago. And we've seen some cases where traffic volumes are off by 2 to 3 times higher or lower than they were 5 years ago. And that's a major problem. And we don't have ground truth data in a number of these cases. And so we're trying to figure out, and it tends to be most pronounced in the rural area of the state. And so it's non-trivial. And the other reason AADT is important when we think about the Meyer database, so for safety, certainly, but also when we look at reporting to the FHWA as a part of the Highway Performance Monitoring System, which is an acronym I've not included here, the HPMS. But every state on an annual basis needs to report its VMT information, right? And that's one of the factors that goes into funding decisions in terms of how much money is dispersed to each state. And then within the state, where that money is dispersed to different counties and different regions, as an example. And so if we have errors of 200 or 300% in the fundamental volume estimates, that's a pretty big problem. And so in any case, I'm going on too long of a tangent here. So I would agree, speed limit, traffic volume. Do we have a third that's particularly important?
Is just the functional class of the roadway important?
Yeah, so there's a bunch of different elements that I'd say we got 2 of the most important there with speed and volume. But yeah, any cross-sectional characteristics, any classifying information. So functional class, I mean, it's somewhat related to speed limit, but I guess functional class and speed limit in combination are probably really, really good and really useful. And then you'd have things like the number of travel lanes, we get into lane width and shoulder width. Those are important, but we'll tend to see that those are relatively consistent within functional classes even. So, but as we look at those, the most important information, I think, certainly would be the location characteristics and the volume. And then at varying degrees, some of those other site-specific characteristics are very useful. Okay, sorry, Mike. So any questions on any of the concept stuff here? So like I said, we're going to have somewhere in the neighborhood of 3 to 5 questions that will just ask you to basically talk through some of the, or write through, I guess, some of the discussion points we just talked through there. So I think you should all be in pretty good shape for that. So beyond that, we talked about a few different network screening methods. The easiest of those is crash frequency. And what are we doing in the crash frequency method?
Just comparing the number of crashes, or how many crashes per year.
Yeah, so basically we've got a number of segments or a number of intersections that are of interest to us, and we want to know which of those have the biggest safety problems. So we just count the number of crashes and we rank them accordingly. As we think about that, there are at least 2 primary concerns with using crash frequency, or 2 pieces of data that may be excluded from that. And what would the concerns be with just ranking segments based on crashes or intersections based on crashes? Let me back that up for 1 second. I said there's one specific element that's not incorporated in the frequency method that would be a concern for both segments and intersections. So what's that characteristic? Or what segments would appear to be the quote unquote biggest safety problem, but may not be?
Ones with higher volumes.
Yeah, so what that tends to be when you look at that rank list, it's gonna, loosely speaking, be a list sorted by traffic volume. The highest volume sites will be at the top, the lowest volume sites will be at the bottom, right? For road segments, there's a second factor, similar to how volume's problematic, but what other characteristic for segments would be a problem and would tend to shift locations up or down that list without necessarily being reflective. So let me make sure I articulate this clearly. There's a factor related to the segments where if we don't incorporate that, we'll see sites move higher or lower on that list, and it might not necessarily because they're more or less safe.
The length of the segment.
Yeah, so segment length is the huge one there. And I forget, I'd have to go back, and apologies, I've been doing a terrible job catching up on grading this semester in both these classes, but I talked to Dr. Gates and he said he had similar experiences, so I don't feel so bad, but the electric grading's tough. But I bring that up because I don't recall when we worked through the homework assignment here, an easy way that this can be addressed is when you use the crash frequency method, is just look at crashes per mile as an example and just sort on that basis. So we don't necessarily, I guess technically you could argue that's a rate, but we generally won't include that as a part of the crash rate method. Well, we'd include it when we calculate the crash rate per million vehicle miles traveled as an example. But if you were just looking at a rank list of segments, you should definitely, even if you're using the frequency method there, incorporate length there. Because otherwise, if you're comparing a 500-foot segment to a 5-mile segment, that's certainly not an apples to apples comparison, right? Okay. And so the next method we talked about was the crash rate method. And so we have slightly different rates for intersections and segments, and we're generally reporting those rates either on the basis of crashes per million vehicle miles traveled or per million entering vehicles. And so does anybody remember how to calculate those respective rates? What information we'd need? So here's the formula for segments. So what are we doing with the segment crash rates? How are those being calculated?
Based on million miles traveled using the ADT and the amount of years and the length.
Right. So ultimately, we want to normalize the risk on a per vehicle basis, right, is what we're trying to do here. And so We take crashes by AADT, and that would give us, generally speaking, the number of crashes over that analysis period divided by an annual volume. Divided by a daily volume, which isn't particularly informative to us. And so we take that daily volume and we want it to be representative of travel over that entire period during which crashes are being observed, right? And so we convert the daily volume to an annual volume by multiplying by 365. If we have multiple years of data available to us, we would then multiply by that time period. And so that would give us, crashes per vehicles over that time period. But then we also need to account for that length factor to make sure that segments of different length are being compared similarly. And so we'd also divide that by the length of the segment. Okay, and ultimately that gives us a number that's really, really small. Typically we'd need to go 4 to 5 decimal places in order to see an integer on the left-hand side there. And so we multiply by 10 to the 6 to put that in terms of million vehicle miles traveled rather than just vehicle miles traveled. Okay. In the case of intersections, it's quite similar. The only difference here basically is that we don't have that length element. And instead of AADT, we have DEV. What's DEV?
The daily entering volume.
Yeah. And how would we calculate that DEV?
The sum of the AADT on each approach to the intersection.
Yep, we would sum the AADT on the 2 intersecting roads, which I think is what you mean there. Because we want to be careful about this because I have seen this mistake made at times where if you added the AADTs that are 2-way AADTs on each of the 4 approaches, you'd have double the actual traffic volume that's entering there. So I just wanted to make sure I think you knew the right answer, but you articulated it in a slightly ambiguous way there. So hopefully you're not offended by my characterization. I may have been off base there, Travis, but okay. And an extension of the crash rate method is the rate quality control method, which we had introduced. And so that setup is similar in nature. So we're calculating crash rates, but in this instance, we're trying to apply basically a probabilistic approach so that we can account for the uncertainty that's inherent in our crash data. And so we basically calculate an average rate across a group of similar segments, and we would determine a critical rate on that basis. And so for an individual site, we would use the site-specific volumes and lengths in the case of segments. That term again drops out in the intersection case. And so this is basically telling us how many standard deviations above the average we would establish that critical value, right? And so in this case, if we set alpha to 0.05, we'd go 1.645 standard deviations. If we set it to 0.025, we'd be at 1.96 and so forth and so on. So we'd have different values we'd sub in here depending upon our specific significance level. And then that would basically take that average rate and it would give us an upper bound on it. This last term here is just I think we talked about this as a continuity correction because crashes are distributed generally as Poisson. And so there's this adjustment factor is just because we're taking that Poisson and we're using it as an approximation to the normal distribution there. But we've gone through and you guys did practice problems in both of these cases. And we had some questions, I think, that were resolved via email basically here. But any questions on the rate quality control method? So again, as an outcome of this step, we don't necessarily see a ranking per se, but we basically classify all of our segments. So we try to identify a subset of sites that experience crash rates that were significantly larger than the comparison sites, basically is what we're doing here. Okay. And then beyond that, the last 2 methods we talked about, both related to the severity of the crash. And so the first of those was the equivalent property damage only method. And so the first way that was presented, this was some work that was done by Kentucky back in the early 1980s, where they basically just had an expert panel assign relative weights to how much, I don't want to say how much more severe, because that wasn't necessarily, from the agency's perspective, we're more concerned with the more severe crashes, in part because there are higher costs associated with them, and we'd like to minimize the number of fatal crashes. And if that's at the sacrifice of some property damage only crashes, that's generally, acceptable to some degree from the agency's perspective. And so these weighting factors were basically developed by like an expert panel. And so this is just consensus rankings from that panel of experts in essence. Okay. And so it does a reasonably good job in that it's assigning, higher levels of weight to those locations that are experiencing higher numbers of more severe crashes. And so those would move higher on the ranked list as compared to sites that experience a lot of crashes, but they might only be property damage. And as an example, there are several roundabout locations in the state that experience a fairly high number of crashes, but they're virtually all property damage only. And so as compared to a signalized intersection, that's a reasonable trade-off when we look at that from a qualitative perspective. Okay. An alternative there is the relative severity index. And we talked a little bit about this, but I don't think I had asked you to necessarily apply this in the homework assignment. So in this case, those weighting factors, instead of being based on an expert panel, we're using actual cost data here. And so the Highway Safety Manual, as an example, has cited a comprehensive cost of $1.5 million, I believe, for a fatality. And so we'd apply that cost for each fatality that's experienced, and we'd have lower costs associated with the less severe crashes. And there are different numbers that are published by the FHWA, by NHTSA, by the National Safety Council, and then individual states also have their own methods for assigning costs to those crashes. I'm trying to think. Here in Michigan, I think they use kind of like a blended approach. Because when you follow this, what tends to happen is you'll see a disproportionate, all the sites that experience fatalities go to the top of that list, obviously then. And so fatalities are important, but there's so much randomness and uncertainty associated with traffic crashes that that's not necessarily the optimal way to prioritize those, because it could just be somebody wasn't wearing their seatbelt in one of those crashes, or somebody was driving drunk, and otherwise that site might not necessarily come towards the top of the list. And so that's one potential criticism here. And so I think the way Michigan does it currently, and similar to some other states, is they'll do kind of a weighted average across these more severe crashes. So Ks and As as an example. But any question on any of the network screening methods? Okay, so we're in good shape there. And then subsequent to that, everything we've talked about over the last few weeks has been various types of before and after type evaluations. Okay, and so the simplest of those would be just the naive before and after study. And so can somebody kind of walk me through, in a naive before and after, what are we doing? How do we conduct that analysis at a high level?
You're just assuming that crashes that would have occurred in the after period had the treatment not been applied is equal to the crashes that were experienced before the treatment.
Yeah, exactly. So we implement a treatment, and we expect if that treatment is effective, it's going to reduce crashes, and an assessment of how effective that treatment is would just be the difference in how many crashes were experienced before and after, right? And so we walk through the method for calculating that. And so it's basically a 4-step process. And so here we're simply relying on raw counts. And so lambda, again, is representing what? Do we remember what lambda is? It's basically
It's the observed after crashes.
Yep, those are the crashes we observe in the after period. And pi is
predicted after crashes,
right? Which in this context would just be the number of crashes we experienced beforehand, right? And we know based on the properties of the Poisson distribution that the mean and variance of a Poisson distributed random variable are equal to one another. And so from that, if we know the mean, we also know the variance. And so using our estimates for pi and lambda, we can determine what the difference, what the delta is in terms of the reduction in crashes due to that treatment. And we can also determine the general effectiveness of that, which is basically just a multiplier, and we've defined this subsequently as a crash modification factor, where we just have the ratio of crashes with the treatment over the number of crashes without the treatment. And so if that theta were equal to 1, what would that mean?
Crashes weren't reduced at all.
Yeah, so basically the treatment had no effect in that context. And when the treatment is effective, that will tend to be lower, i.e. less than 1. And in some cases, it may be ineffective, or maybe for certain subsets of crashes, you may see some increases there. And so it's conceivable that you could also have values greater than 1, which would indicate that crashes actually went up in that setting. And then to determine whether or not these differences, whether the crash reduction or the index of effectiveness are statistically significant, we'd want to be able to calculate the variance or the standard error of those terms. And so in the case of the difference, we would just add the respective variances of the before and after crash counts, take the square root, and that would give us the standard deviation or standard error of this estimate. And so roughly 2 times the standard error would give us a 95% confidence interval, and we'd check whether or not that confidence interval included what value?
Be 0.
Yeah, so if that confidence interval includes 0, we wouldn't be able to claim a significant difference at 95% confidence. And in the case of the index of effectiveness, basically this is a ratio, and so we multiply the respective variance terms there. And so what this is, it's just theta squared, and then this is basically the right side here. This is analogous largely to how we incorporate sample size into our standard error calculations when we're testing means. So this is just like 1 over lambda and 1 over pi respectively, just like we'd have 1 over n1 and 1 over n2 in the case of some of our tests that were introduced in 849. And then what we'll tend to do, this minor correction factor down here, is just going to basically be reflective of the fact that this will tend to be biased, slightly biased. It will tend to overestimate the effectiveness, but as our sample size increases in terms of the number of crashes, we'd expect to see in the after period, then that weight goes down significantly. And so this is basically just a scalar that in this quantity will just converge towards, basically converge towards the numerator here at large sample sizes. Okay. Any questions on the naive before after stuff? Okay. We can also introduce a before and after with control. And so in this case, what's the primary difference that we're accounting for?
Any changes that would happen in the crash data, not because of the change that we made?
Yeah, so basically this would be all of the other factors external to that treatment that are also influencing crashes between the before and after periods, right? And so we may see that crashes have gone up, and so had we not accounted for that fact between the before and after period, we would actually be underestimating the effectiveness. Or conversely, we may see the case where crashes are generally trending down, in which case we would overestimate delta in that circumstance. And so the primary key here is we're just trying to figure out how much crashes are shifted up or down by in the after period, and how do we determine that slope there? Basically, what are we doing?
Comparing the number of crashes that occur in the after period at the control sites to the before sites, and assuming that same change will happen to the study site.
Yep, exactly, right? So we have a set of control sites that we presume are similar in nature to our study or test sites. And so we would just take basically N over M in this case, the number of crashes after the treatment at the control sites over before, and we'd assume that same ratio would apply at the treatment sites, right? And so calculation of those quantities is very similar to what we've seen previously. So as before, lambda after the crashes have been implemented, we're just counting the number of crashes that occurred at the study site in the after period. That multiplier again is just the ratio of sites between the after period at the control site over the before period at the control site. And so our estimate of crashes in the after period is just the count of crashes we would have in the before period at the treatment site times whatever that multiplier is, right? And so the implicit assumption we're making here is that those rates are the same between the control and treatment sites. Now, we don't actually know that because the treatment's been implemented, right? So we have a confound there, but that's as long as those control sites are selected in a rigorous manner such that they're representative, that's probably a fairly safe assumption for us to make. Okay. And then the variances as before, in the case of just the counts for the after period, our mean and variances are equal to one another. And in the case of the expected number of crashes, we do have a subtle difference here. And so in calculating this, we would take basically pi squared times 1 over k, where again, k is the number of crashes that were experienced in the before period, plus this adjustment factor here, which is just roughly equal to 1 over m plus 1 over n, which would have been this is accounting for the variability in that rate estimate that we're accounting for, okay? And so from there, it's straightforward. We use the exact same methods that we had in just the normal naive before and after study design to calculate delta, theta, and their respective variances. Make sense? Okay, and then we also had the EB. I'm cringing because I would have introduced the cross-sectional previously because it's similar, but we'll go through the more complex method first. So in the case of the empirical Bayes method, what are we doing from a big picture perspective? So I guess that let me preface that in all the cases that we've talked about, our after period crashes is just always based on whatever that crash count is, right? And so the question, our expected crashes without the treatment are determined how in this case?
There's some function that's created based on a reference group that's used to make some rate to increase or change the amount of crashes that would be experienced, and that's compared in like a weighted average to the observed after crashes.
Yeah, exactly. So apologies, because I realize we've got at least 2 different sets of variables we've introduced here. But what Jordan's largely referring to here is this weighted estimate that we see right here, where we're taking a weighted average of how many crashes are experienced at that site in the before period and how many are predicted to have occurred during the before period based upon data from a control or reference group, right? And these 2 adjustment factors you see here, so we calculate that weighted average, which instead of putting us up here where we'd be in the traditional before and after design, that's typically going to be dragged down closer to the reference group, right? And then we're basically adjusting that using 2 different factors here. So first of all, TA over TB, does anybody recall what that's referring to?
The time in the after and before period.
Yeah, so that's the time period. If you look at the Highway Safety Manual, it generally recommends 3 years before and after. And so if those time periods are the same, obviously that factor just drops out. It's equal to 1. And you'll probably run into this, and I don't want to give too much away on the midterm. But you're going to have a case there where your before and after periods are different, in part because we don't have complete information for the after period. And so if that's the case, you just want to make sure that you would scale those estimates appropriately. Okay. And then the other adjustment factor that's introduced here, does anybody recall what this is representing? So this is basically a second adjustment factor to account for the differences between those two periods. And so what we're doing here, we're basically taking that regression model, that safety performance function that had been estimated, and we're plugging in the input data from our test site during the before and the after period. Okay. And using those data, we basically then are going to have an estimate of how much crashes are increasing or decreasing by based on the control sites, based on a model that was estimated from the control sites between the after period and the before period. Okay, so that's just basically telling us the slope of those differences. Okay, so the first step here, when we compute that weighted average, that's just giving us a weighted average for the before period, and so we need some way to project that forward to the after period. And the way we're doing that is that we're using the regression equation, we're plugging in the input for our test sites during the before period, plugging in the data for our test sites for the after period, again, assuming the treatment hasn't been applied. And what that typically is going to capture would be changes in traffic volume, because there's probably not much else in that SPF that would change between those two periods. And so it's very similar in many respects than what we're doing with the BNA with control type evaluation there. Okay. All right. And so, yeah, this is just basically walking through what those various parameters are that we had just described previously. And so it's fairly similar and straightforward. To determine that weighted average, we would need to first estimate a regression model. And so you're getting some experience with that right now. So we're typically going to estimate this in the form of a negative binomial model. And so we'll have this general functional form here. As an output of that analysis, we'll have estimates for what that vector of betas is essentially. So we'd know the intercept and the slope term for each of the predictors in that model. We would also, as a part of that output, have an over dispersion parameter. And that over dispersion parameter is important because that gives us guidance in terms of how much weight should be applied to the site-specific crash counts versus the output from the predictive equation, right? And so that weighted average is calculated as shown here. So basically, we'd take the expected or the predicted number of crashes here times that alpha, and we'd multiply that times what's predicted by the equation. And then 1 minus that weighting factor W is multiplied by the actual crashes that we experience, okay? And so generally speaking, we give more weight to the site-specific data when two conditions are true. Either that model is very poor from a predictive standpoint, and so if you got a large value of alpha, we'd have more trust in the site-specific data than if we had a better fitting model. And then secondly, as the predicted number of crashes gets larger at that given site, then we would have less concern with regression to the mean, because if you're averaging 50 crashes per year versus 5 crashes per year, regression to the mean is going to be a greater concern at the 5 crash per year site. And so we'd also tend to give more weight to the site-specific data when we have larger numbers of crashes or larger time periods to work with, right? And then the variance of that estimator is just 1 minus the weighting factor times that actual weighted average that we've calculated. Okay. All right, and then from there, like I said, this ratio is just a comparison between how many crashes we'd expect to see between the after and before periods using the data from the study sites. And so that's telling us what the slope, what that shift in predicted what that shift in expected crashes is between the before and after period, and we take all that information in combination to arrive at this estimate for pi, okay? And then from there, steps 5 through 8 are identical, with the exception of this minor difference in how we calculate the variance of pi in this circumstance. But otherwise, everything else is as we've seen before. So any questions on the EB stuff? Okay. And then the last method that we had talked about this Tuesday, so I'll just go through this really quickly. Cross-sectional evaluation is just used in circumstances for when we don't have access to before period data, and that could occur for a variety of reasons, the most common of which is that the agency just doesn't have records of when specific treatments were installed. And so in that case, instead of relying on the before period count, we're just relying on an after period count from a group of similar control sites, okay? And so the biggest concern here is what from an analytical standpoint?
Doesn't account for regression to the mean.
Yeah, and so we'd want to make sure that these control groups are as comparable as possible to the treatment sites in applying this. But the actual mathematics here are basically identical to what we saw in the naive before and after, except instead of using the site-specific before data, our estimate of pi is now just whatever the average is from those treatment sites, okay? And so if the treatment sites are well selected, this will give us a fairly good estimate of what the effectiveness of that treatment is. If there are differences, that will also be reflected. And that's something you might want to be mindful of on the midterm. Hint is that there's a specific quirk we're going to run into on the midterm where you might not necessarily want to use all of the control sites. So you'll want to try to think through which sites should or should not be included there. Okay. And so as opposed to just taking every potential control site, and I think I used the example, but I can't remember what I've talked about in this class versus 849 versus my research group meeting. So I'll just restate it here. If we were looking at crash data on the 2-lane highway network and we try to do a comparative parallel study for where speed limits were increased or where rumble strips were installed, we wouldn't necessarily want to take all of the untreated sites as our control group, because in both of those cases, we're only installing those treatments on the high speed, so 55 mile per hour and above road network. So you wouldn't want to include all the small towns and all the speed reduction zones in those. And there'd probably be some other factors you'd want to match by. So as we think about trying to identify good control sites, any thoughts on what variables we should try to match by in selecting those control sites?
The speed, I guess like the amount of like horizontal curvature within the area. I don't know if that really applies.
Yeah, so ideally we'd like to try to match by geometric characteristics. That tends to be somewhat challenging, but I would say speed is one. Speed is one of two that I would be very careful to try to match by. Beyond speed, what other factor is going to have a very pronounced impact on our safety performance?
Probably the traffic volume and length, if it's a segment, is important to compare.
Yeah, exactly. So those are the primary concerns. So it would basically be length, volume, and speed would be the three most important there. And so there's been some literature that's looked at different methods for trying to match, and that would include things like you could estimate a logistic regression model as an example, to try to distinguish factors that would be similar or different between your samples. But for our intents and purposes, I'm fine with a more qualitative approach. So as an example, if you have significant differences in traffic volume, that would probably give me pause in matching. And if you have significant differences in speeds, that would also be a bit of a concern. Now, segment length, that will largely probably come out in the wash because you're generally looking at your treatment and control sites are just going to be based on the characteristics of the road networks. Those should be reasonably consistent. So speed and volume are the two you'd want to match by particularly. Okay. I think that's, oh, and then maybe this is my last slide, or maybe I have one more after this. So across any of these approaches, whether it's the before and after, the DNA with control, the EB, or the cross-sectional, in all those cases, we can sum both across sites over time, or sorry, we can sum within sites over time, and then we can also sum across sites. And so those means and variances of the crash counts are additive in those cases. Okay. All right, and then I guess the last slide I had just related to SPF development. We've covered this pretty extensively, and so what we'll generally see is that we'll have models in the form as specified here. So we'll estimate these as negative binomials. We'll log the traffic volumes and the lengths, and we'll typically, in the case of segments, treat that length as an offset. Okay. And then any of the other characteristics that are also influencing crashes, we can estimate parameters to account for those influences as well. Okay. Now I think, yes. So the last homework is due this weekend, and then the midterm will be next Tuesday. And so I don't know if either of you have any additional questions at this time. Okay, so I think I've got all the videos up for both classes. I'll try to get this one up. I've got a break here now until lunch, and so I may edit out the part where I let my dog out to chase squirrels, but we'll see how that goes. So I'll have this up shortly. Okay, guys. All right. Have a good one.
Good. Yep. Thank you.
Bye.
Yep. Bye.